Okay, hello, everybody. Those online and those here in the room, welcome to the August meeting of the Howard Astronomical League. We have all sorts of good stuff to talk about and an excellent speaker tonight that I'm excited about. So without further ado, let's just go ahead and jump into it. First thing is introductions. Is there anybody new in the room that would like to say hello and welcome? Please.
My name is Michael Frank, and I just signed up a couple weeks ago.
Great. Welcome. Yeah. Are you new to the hobby, or you
Well, I used to work at Goddard,
okay?
and I know Salman Sheikh.
Oh, okay.
He works there, I believe. And I remember the name anyway.
Okay.
And I worked there. I worked in the fitness center,
Okay.
so I really wasn't a civil servant. I was a contractor,
Okay.
but I've met a lot of people.
Okay.
down there.
So
And it's very interesting. And I have a telescope. I don't use it that often.
okay,
So I'm basically here to learn more about.
you've come to the right place.
Okay,
You'll find a lot of people here who just love to share and enjoy the hobby. They love to share what they know. My recommendation is go to some star parties. Members star parties in particular is when people have time to talk. Usually the public ones, people are out and about sharing views with the members of the public. But come to meetings and come to events and you'll pick up a ton. I did too. That's how I got into this several years ago. Anybody else? Oh, Tom.
Hi, I'm Tom T. It's nice to be here for my first HAL meeting. I've been enjoying the star parties out at Alpha Ridge and enjoying meeting everybody in the club. They're very welcoming. I think we're really blessed that we have so many people with technical backgrounds. I don't know whether it's proximity to Goddard or what have you, but there's a tremendous knowledge base that I'm seeing.
I've thought to myself that it's a blessing and a curse. To be in an astronomy club here, the light pollution is, an issue. But the fact that we're so close to the Space Telescope Science Institute in Baltimore and Hopkins and Goddard and,
Indeed.
so we're able to get some fantastic speakers. So yeah, good. Welcome.
Well, thank you.
Pat Chart. I've been a member for years. I've never gone to the meetings because I'm an hour away. It's been, I'm a science teacher. I've been teaching science for 48 years. And one of the things I teach is astronomy to sixth graders.
Wow.
So I have a high interest in observing. And as I say, I come to the Alpha Ridge, but I never really come to the meetings because of the distance.
Yeah.
At the same time, I'm trying to stretch my knowledge base because I do mostly planetary and lunar and trying to get into the deep space.
Cool.
Yeah.
Yeah.
I'll say one more thing, and that's the sixth graders actually have a series of 12 telescopes I line up like library books. They're 4.5 inch Newtonians, fairly fast 500s, but they have parabolic mirrors and a decent mount. And the kids, have an opportunity to kind of enjoy the night sky. And again, I really emphasize they start with lunar and planetary because, of the nature of the skylight and everything else. But
So where
I'm
do you
looking to
teach?
stretch my knowledge.
Right, well, we came to the right place, but I think this could be a two-way street because we do a lot of outreach, and so some of the learning materials that you use might be of interest to us too. So that'll be good. Maybe we can talk a little after, after we go through the meeting. But which way? Where are you?
I'm in Potomac, Maryland.
Potomac. Okay.
Yeah, private school.
Okay. So there's another club very close to you.
The national capital.
Yeah, those, and then we can talk offline.
Yeah, but they don't really do a lot of observation. You have to go all the way to University of Maryland Observatory and stuff like that. So,
All right. Well,
yeah.
welcome. I'm glad you're here. Definitely want to talk to you after the meeting. Okay. Anybody else want to? All right.
I'm new. This is my first time here. I was a member of Delmarva Stargazers for many years. Did a lot of observing in Tuckahoe.
Great.
And kind of took a hiatus, I guess, when COVID came around. So I'm hoping to get back into observing. I got a 24-inch Dob.
Oh,
Oh,
nice.
we're hoping to get back to them sometime.
Yeah. Gone to Winter Star Party a few times.
Oh, yeah.
Has anybody done that? Yeah, it's nice. Winter Star Party.
Yeah.
And I also used to teach astronomy at Anne Arundel Community College. I did the labs out there years ago.
I love it. Welcome.
Yeah, I'm hoping to get back into it. It's kind of rusty.
Oh, well, I'm glad you're here, and we hope to see you at more events and star parties and whatever. So, and maybe we can also talk a little after the meeting. I'm curious to just talk a little more. Okay, great. That was a lot of new folks. So, recent events and public star parties and scheduled star parties are listed here. We've got one coming up. We just had one, and it on the let's see, did I circle the right month this time? Yeah, I did. So so we've got one coming up on the 7th, members only. That would be a good one for just like talking to people, and then another public star party on the 14th. We've had a number of impromptu events recently. I don't have pictures yet of the last start party, the one on the 10th. But the one from the month earlier, there's a couple of shots. Notable is Crystal's red activities tent, which is, I haven't seen in person yet, but I'm looking forward to learning more about that, and maybe the club will get one too. Anyways, that's it for recent events. One other thing I wanted to mention, upcoming events, is that not next month, but the month thereafter. So this is the August meeting. The September meeting will be here. I'm sorry, where are we? Yeah, this is the August meeting. Sorry, the September meeting will again be held here. The October meeting, it's not all definite yet, and I don't have all the deets, but we are probably, we're planning to hold the meeting at Howard County Public Library, and the guest speaker will be astronaut who has written a book. His name is Tom Jones. He just wrote a book about his experience being on the ISS and whatnot. So I'm personally going to bring my own copy and ask him to sign it. But more detail coming. I just wanted to give you a heads up that that's in the works for October, not September. September, we have an excellent speaker from NASA who's going to talk about she's going to talk about the moon. So what else is upcoming? Anybody have any good things? There was just a conjunction that was pretty cool. The Jupiter-Mars conjunction. And then of course the showers, the meteor showers that just happened.
Jupiter was spectacular.
Yeah, yeah.
The weather's not great, but I'm planning to have a public star party tomorrow, the 16th at Glen Oak Country School. I'll have my activities tent and my students will do some presentations. The sky's going to be pretty patchy, so pretty similar to the public star party. But yeah, everyone's welcome to attend if you'd like.
Thanks, Crystal. And I think that there's more detail in an email that you sent out to the distribution of the Howard Astro. If anybody wants more than that, talk to me afterwards, or we'll put you in touch with Crystal. Thanks. And speaking of Crystal and her awesome activities tent, the next item up on the agenda is the book of the month. You want to take the?
Yeah. Can everybody hear me okay?
Yes.
Great, thank you. So today's book of the month is Women in Space, 23 Stories of First Flights, Scientific Missions, and Gravity-Breaking Adventures by Karen Bush Gibson. So the hardcover edition was first published by the Chicago Review Press in 2014. The paperback copy that I've purchased for our library here was made available in 2020. So Women in Space is actually part of a larger series called Women in Action. It's a biography series that introduces younger readers to women and girls throughout history. This particular collection highlights the accomplishments of women as pilots, physicists, doctors, and much more. as they joined humanity's first steps into space. Each of these 23 stories introduces why it mattered to be the first or how each person tackled the challenges of their missions. The language of the book aims to be as accessible as possible, so the technicalities of any of the scientific missions are pretty largely absent, but it's a great read, and the chapters themselves, I'll say, rarely contain direct quotes or references to how the women directly recall their experiences. So I would caution that the stories do not provide a complete picture of their personalities or the overall characters. It is a collection of very brief biographies, after all. I would recommend maybe reading this in one or two or three of these stories at a time, mostly due to there's kind of like a formulaic storytelling style. This is intended for audiences 12 and up, so it is more a young adult novel. Overall, I recommend Women in Space is a great addition to the library. It's a quick and easy way to learn some basic facts of these women's careers, missions, and the impact they had on history. It will be available for checkout at the next public star party, so you're welcome to find me in my activities tent or come into Halo and you can check out Women in Space.
Cool, awesome. Thank you. I think I'm gonna be polite as president and not jump in and do it right away. I'll give other people a chance, but I think I'm gonna get that for my daughter, high school aged. I'm gonna check it out. Literally check it out. Okay, thank you. And next on the agenda is our featured speaker, is Dr. Sachin Shenoy. He's going to talk about SOFIA, the last flying observatory. Okay, my text is too small. I can't read all the stuff that I wanted to say about Sachin, but I just wanted to say that his resume is very impressive. His history of work on Hubble and James Webb. I think most all of his work was in infrared stuff, and we'll be hearing more about that with the SOFIA. And he also likes to study molecular clouds and the chemical properties and physical properties. And that we also in this club love molecular clouds. We just like taking pictures of them and making them as pretty as we can. So other than that, he's a volunteer. He loves the outdoors, a bird watcher, and enjoys cooking and traveling and long distance running, which is super impressive. So I'm going to allow him to share the screen, and then we'll hear from Dr. Shenoy. You ready? Yep. All right, we should be able to grab the screen.
I did.
Are the people online seeing the screen?
Yes.
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 I just need to figure out how to make us see the screen here. All right, and I just need to move the mouse in the right place. Sorry about this. You'd think I would have this down by now. Okay, I think we're good. Is that full screen? Full screen.
All right, can people online hear me okay?
Yes.
Oh, there you go. Okay, good. So thanks everyone for inviting me to give a talk. As Victor was mentioning, I now work at Space Telescope Science Institute. So normally I'll talk about James Webb or Hubble or something of that sort. But I checked out some of your talks in the past, and it looks like you had people who talked about those things. So it didn't make sense for me to talk again about the same thing. So I thought I would talk today about something I've been really passionate about. I've worked with this mission for about a decade or so. And that's SOFIA. And before coming to SOFIA, I had the good fortune to work with Spitzer Space Telescope. I've worked, as I said, with Hubble a little bit, now with James Webb. So I'm a pretty lucky guy. Couple of things before I start. I tend to get excited when I talk about astronomy, so I'll be jumping around, walking around and things. Sometimes I also speak very fast, and you will notice that I do have some accent. So if anyone of you don't understand anything what I'm saying, just stop me, say, hey, cool down, explain it to me. Or I may have a way of explaining that doesn't make sense to you. If that happens again, stop me and say, hey, can you explain it better so that I didn't get what you meant? Let's keep it really informal. So don't wait till the end of the talk to ask questions. If you have a question, just stop me in the middle, it's fine. That way we may go a little bit over time, but the questions get answered. Okay, so let's get started. SOFIA, for those of you who don't know SOFIA, we astronomers love acronyms. So SOFIA is an acronym for Stratospheric Observatory for Infrared Astronomy. And what that is we just took a 747 plane, one of your intercontinental planes, chopped off one side and put a 2.5-meter telescope in it. And from outside, it looks like a normal plane. It just flies, it has tires, it does the same thing, goes up to 40,000 feet and so forth. But the fun thing is, up here, probably people will see my cursor. Up here, you'll see there's like a bulge at the back of the plane. And that is the modification that we had to make to keep the telescope inside. You'll also notice that on this plane, there are two flags. One is US and the other one is Germany. And that's because this project was pretty expensive. It was about 80 million a year. And 80% of the funding came from NASA and 20% came from DLR. So you'll see that I have icons of DLR on the corner of my screen to acknowledge their contribution. DLR was the one who built the telescope, who refurbished the plane. So it was a really nice international collaboration between two countries, two different set of scientists to make this mission a success. And if you go in that place, that thing that's like a big garage door that opens up. That garage door is about 15 feet by 23 feet. So it is gigantic. So it opens up, and once you open it up, you'll see inside that there's a mirror, which is a 2.5-meter mirror. There are a couple of modifications right here in this image, which you will see. And the first one you'll notice is all those hair-like features that is around the telescope, these things. So what happens is we go up to 40,000 feet, we are flying at 0.8, 0.9 Mach, and the airflow that is on top of it is pretty turbulent. So what we do is we have this what I don't know the technical term, this hair-like things, which breaks up those eddies and makes the eddies smaller. So the wind that is on the wind that flows on top is planar rather than swirling around, right? So that is number one. The second thing you'll notice that in the back here, there is a baffle. So if you have a big object, open object that is flying in space, that there's a tendency of the air to go in. So what this baffle does is instead of the air flowing in, it just hits this and flows outside. So the reason we do all this is we want to have as much planar flow of air on top of the telescope as possible, so that we reduce all the seeing. Basically, we are trying to improve the seeing by keeping the air flowing in a planar fashion.
So the telescope's completely exposed to the moving air. There's no light barrier. And so you have a depressurized section then.
Yep, I'll be showing that in a second. But before we go to SOFIA, I need to remind people that SOFIA, in a sense, SOFIA is not unique, right? Like, yeah, it's a flying observatory. So what? We have had those before. And in the 60s, we had Learjet. It was a tiny plane. The telescope was really tiny. One of us could just lift it and stick it up on the window of the plane and go fly around and take pictures. But then we got greedy, astronomers. We want bigger telescope. So we moved a bigger one, which is called KAO, Kuiper Airborne Observatory. That was a bigger, about a meter telescope. And now it had its own section in the plane where it could sit and could observe the universe. And then in the recent years, we came up with SOFIA. Now it's a 2.5 meter telescope. It's a 747. And in the past, when I used to give this talk, I was so proud about the work SOFIA did, and I had expected that airborne astronomy in the world would have a very bright future. And when I was talking to my students, I would say, so this is now, and then in 2030, we'll have Airbus 3800, and we'll have a 4-meter telescope inside. But after what happened with SOFIA, I turned a bit pessimistic about that outlook. But we'll see. Who knows? Who knows? Maybe we'll have a bigger and better observatory in 20, 30 years. So there is an image of Kuiper with its door open. And here is an image of SOFIA and Kuiper together. This is at NASA Ames Research Center in Mountain View, just south of San Francisco. That's where SOFIA's Science Center was based. And once in a while, SOFIA would come there and people would visit, and you'd see the line going out the plane, out of the building, all the way back to Timbuktu. Because people were so interested in this mission that it is something that flies, not maybe in space, quite high up, and they could come physically see it and touch something. So it really, people were really curious to come and look at us and see how it works and how we make this work. This is really a marvel of engineering. So a brief history of SOFIA. SOFIA, the plane, started with Pan American World Airways in 70s. It was designated as 747 SP for special performance. So these are the stubbier version. These are the shorter version of the 747 classic plane. And it was christened as Clipper Lindbergh. It was with Pan America for about 10 years. Then in 80s, United Airlines bought it and they operated it for another 10 years. So after 10 years of service, NASA bought it and sent it to Waco, Texas to be modified so that we can use it as an observatory rather than shuttling people back and forth. And this was never done before, as you can expect. And we didn't have one plane, we had 2 planes sitting side by side, so that if something went wrong with the modification we were doing, we could go back to the other one and see how things work. So we had a whole full 747 sitting side by side with it. Okay. And then in 2007, we had the first flight over Waco, Texas. That is, all the modifications were done. The telescope was inside. All the ballast that needs to balance the telescope was inside, and the flight was done, but the outer door was not open. This was just a post-modification flight. We did that. And then it came to NASA Dryden Flight Research Center in Palmdale, California. And that's where it stayed for the next 10, 15 years. Dryden is recently named as Armstrong, so now it's an Armstrong Research Center. And in 2007, it was rededicated by Eric Lindbergh. And on December 2019, for the first time, we flew over the California skies and opened up the side of the plane, on the side of the telescope to look outside. And everyone here has seen Hollywood movies, and as soon as someone shoots a gun in a thing, everything explodes, and that doesn't happen with SOFIA, fortunately. Because as our gentleman teacher was already talking about it earlier, the telescope that sits in the plane is isolated from the rest of the plane. There's a pressure bulkhead. So on the one side, we could comfortably sit and work. Well, comfortable is in quotes. We could sit and work, whereas on the other side, the telescope was exposed to space and it would look outside. And I do have a short video here to show. This was the first time we were trying to open up the. So here is SOFIA flying for the first time, and there is a Air Force pilot with a fighter plane sitting on the side of it, watching the Of course, it's not gonna work now. There it is. I'm gonna move it a bit. So the fighter pilot is flowing by the side of it and he's taking the picture, and now you'll see that the side of the plane is slowly opening. It just looks like your normal observatory. We are just opening the shutter to start our observing. But this was done for the first time in 2007. And the pilots of SOFIA are all NASA pilots, and they were extremely nervous because they all had seen the Hollywood movies and they were expecting the plane to crash. But the engineers on the team were so confident that they were like, nothing is going to happen. We are going to open the door. We are going to start observing. And that's what we did.
Is there a camera that looks at the telescope to make sure nothing is amiss?
We had some cameras sitting in there that we could monitor to see what happens.
Yeah.
All right, back to the doc. So that was in 2009. In 2010, we used the instrument forecast to look at Jupiter and M82. That was the first flight of SOFIA. Again, we were very proud, we got excited, but we didn't know to what height SOFIA is going to reach. And hopefully by the end of this talk, I'm going to convince you that just observing Jupiter and M82 was not a big deal, but we did a lot more than that. In 2012, cycle 1 science operation begins. And in the August of 2012, I joined SOFIA and I made SOFIA great again. I'm sorry, I didn't mean that. I couldn't help it. In 2013, it was the first time we went to the Southern Hemisphere to observe the Southern Hemisphere. So what we decided to do was in our summer, it's winter in the Southern Hemisphere, the skies are better. And we get access to the galactic center, which, as you know, galactic center is very low in the horizon here. But if you go to the Southern Hemisphere, they're high up, and galactic center is a very important place to study dust and gas in our galaxy. So SOFIA is a simple Cassegrain telescope, which I don't need to tell this audience. You all know what this is. So we have the primary, secondary mirror, and then the Nasmyth tube, where on the other side sits a science instrument. So we could put any instrument, we could remove them, we could exchange instruments. So it had an advantage of, like with the space telescope, once the space telescope is gone up, the instrument are all set. You cannot change. You can change the 3 instruments that already is. But if, say, in 5 years, you develop a new instrument, you can't go ahead and put it up on the space telescope. But with SOFIA, you can do that because SOFIA lands every morning back at home base, and then we can go up, remove the old instrument, put the new instrument. And here,
747s is so big. Is all that space used? I mean,
you'll see.
okay.
You'll see. So this is the inside of the telescope. We are looking at the back of the telescope. That black thing you are seeing here, that's the Nasmyth tube. That's where the instrument would sit. That whole thing is a tube that goes inside and connects to the telescope. And you will see that there is sort of, the tube is so big. Okay. So there's a well here. So the telescope sits in there. So the entire plane, the surface of the plane, is basically a stuff that holds the telescope together. And just to give you some contrast, there is a gentleman inside the well standing looking at it. So you can imagine how big this thing was. And one of the questions we always get asked was, you are in a plane, you are moving at 0.7 Mach, we all have traveled in plane, there is so much turbulence, how do you stabilize the telescope? And there are few technologies were there that we use. One was these black things that you see around here. Those are pressure dampers. So those are the first, if you want to say, first order of vibration isolators. So those are like this huge tires filled with pressurized gas, and it basically works as a dampener. So if it moves. The second thing is that entire blue thing that you see here, this whole thing is a bearing. And when we reach 10,000 feet, we will flood the bearing with oil. And what that does is it lifts the entire 2.5-ton telescope off the body of the plane and isolates it from the plane. So now the telescope is in its own inertial system. And no matter what the plane does, once we track a star with our gyros, it just locks on. And it's a bit hard to explain it in words, but here you can, maybe I can show. So I'm sitting inside the plane. We are sitting inside the plane and looking at it. And you'll see that the whole telescope is moving. And you're gonna wonder, what's that?
Is that in real time or is that,
It's a time lapse.
but it's not sped up? That's how.
No, it's not, yeah, it does move at that speed. I can replay it. Yeah, it does move at that speed.
Wow.
But what you need to remember is that this image, this video is taken from inside the plane. So it is not the telescope that is moving, it is the plane that is moving around the telescope. Does that make sense?
Yeah,
Yeah.
absolutely.
So once you're locked onto your whatever star you are observing or your target, telescope is there. The plane can do whatever it wants, but the telescope is gonna stay.
Got a question, so just mechanically, why do you flood after you're up, why can't you just have it flooded before you take off even?
I'm not so sure it had something to do with the temperature of the oil. Because the reason I know it's the temperature of the oil is, again, I'm not an engineer, I'm an astronomer, so I don't know the engineering part. But when I'm sitting in the plane and when I have to listen to people, they're like, there's always this talk about, oh, the temperature is too high today, so we need to wait for a little bit, or it's too cold and we need to wait. So there was something to do with temperature. And my guess is, it needed to get a certain temperature to have a certain viscosity so that it is thick enough that it would lift. So
What altitude are you flying at? I mean, the temperatures would be 100 and something below, and that's probably the temperature factor that you're talking about.
that's right. That's why we have to go up to 10,000 feet. So it's
10,000.
cool enough and then we can go. But our operating altitude is anywhere from 35 to 50,000 feet.
Did
Yeah,
you have to gradually, like slowly get to that altitude to allow the optics to adapt?
Yes, yeah, but
Okay.
I'll come to that in a bit. Yeah, these are all astronomers asking astronomy questions. I should have known.
The real astronomers want to say, were you using PhD guiding to guide your study?
About the oil slashing in there.
No, I won't slash in there because it's a very thin layer. I mean, it's just a millimeter layer. It's very thin. It's not a big thing of oil there. So, yeah, anyway, this is a cutout of a plane. And as you can see in the back, there is a telescope. That's the pressure bulkhead I talked about earlier. So the telescope part of it is open to space. But then the front of the telescope is pressurized, and that's where we would sit and do our work. Those are the different sections that have been listed. There is let me see if I have my cursor. I'm hoping oops. So that part is where the telescope operator sits. This is where the science instrument operator sits. This was the data analysis table. Here we have the mission directors, the main cabin, and we also have educators systems. So SOFIA always had a program where we took educators from US and Europe, and we flew them with us. And the idea was they would come with us and they'd learn how research is done in real time. And they'll take that experience back to schools and teach students about what research is. We basically wanted to show them not all researchers wear lab coats and have very thick glasses. We are cool people, and flying in plane, taking pictures of the universe. Here is another cartoon version of what SOFIA looks like. And as again, we had a question earlier saying that how much space is there in this image? It looks really beautiful. There's a lot of space. It's clean. It looks like a 5-star hotel in there. It isn't. Telescope in there, people walking around. And that is the blue thing you're seeing right next to the telescope is the bearing I was talking about. That's the one that's holding the telescope. But in reality, this is what looked like inside the plane. It's very crowded. It's filled with instruments, tons of monitors monitoring different things. And as you can see listed there are the telescope operators. Their job is to make sure the telescope is working. That means they are the ones who will point to the target make sure that they are on the tracking star and the star is being tracked so the telescope stays stable. Then we have the instrument team whose job is to run the instrument. Once it is locked onto your source, we start collecting data, and we may do images or we may do spectra. We'll talk about that more. So that's the part of the instrument team. The team on here, right in front, this is the data analyst table. So most of the time I would be sitting either here where the blue jacket gentleman is sitting, or I would be on this seat here working with the data. And then in the back here in the corner are the mission directors. They, she, he are the god of the plane. So we didn't do anything without their permission. They controlled everything. Because if you let us astronomers run the plane, we'll probably want to try fly upside down and look at something else. So they never let astronomers do anything. We couldn't talk to the pilot, for example, whatever had to happen. They were the conduit. So we would tell the mission director, we want to do this. And they'll say, okay, permission granted, we'll go, we want to move the telescope, whatever. We always talk to them. The same way the pilots, if they had to change direction, they would talk to the mission directors would tell us. So they had power. Question in the back first? Yeah.
Well, I just 2 points. So I was in the Air Force and I flew on reconnaissance planes, and we had an airborne mission supervisor, and they were the god.
They were the gods.
Yeah,
We do what they tell us to do.
Yeah. Now, you mentioned tracking a couple of times. So you want to talk about tracking? Because it just can't be the telescope. Is the aircraft also flying an orbit, or?
Yes, I'll come to that.
Okay.
But the tracking that I was talking about is mostly tracking the source. So we have the big telescope, the 2.5 meter telescope on Earth. But on the side, we have tracker telescope. We have 3 of those.
And how much movement do you have inside that little 12 by 15 window?
2 degrees.
2 degrees.
2 degrees. We
Yeah.
could move about 2 degrees.
So
and
over the course of the night, that could be more degrees, couldn't it?
yeah, but there is a technique to observe, which I'll mention in a bit. But the tracker is that we take the data from the tracker, feed it through our gyros, and make sure that the star stays in the pole side, wherever we are. And that's the tracking I'm talking about.
Yeah,
yeah.
So does that mean that if the object you're imaging starts to, set, I don't know how many hours would a flight?
10 hours.
10 hours.
10 hours.
So if it starts to, would the plane just fly and start to angle? Would you have like a?
So here is our what happened on a given night. So we would start from Palm, we would fly out, and on top there, you'll see we have those numbers. We call them legs, flight legs. So the flight leg was first takeoff, then we do observe delta left, that is a calibration start. Now we are on the Orion leg. Once we finish Orion, we have to turn the telescope because the next object we observe is NGC 414, which is on the other side of the star. So if we had to observe sources from different parts, we had to move the plane and then observe that for that given amount of time. And then we turn again. Now we are on IC 2233. We turn again, we do a couple of other stars, and then we come back to base. There was also a question earlier, do you all fly all the way up front? And you'll see that on the plot that is plotting there is the altitude of the plane. And as you'll notice, when we start, we go up to our observing altitude, which is usually around 36,000 feet. And that's where we start observing. But as the night progresses, we keep going higher till we reach about 43,000 feet, and then we land back. Does anyone know why we use this particular method? Why don't we go to 43 directly?
Needs to outgas.
Not exactly. I'm getting there, maybe.
Is there temperature differences for the?
No.
Pressure?
What?
Pressure?
Pressure, no. It's just gas. The fuel is so heavy when we start that it takes really a lot of energy to fly up there. So what we would do is, depending on the instrument we had, some instrument could be observed at a lower altitude, but some instrument couldn't just because of the physics. We had to go to a higher altitude. So we would start at a low altitude, and as we burned fuel, it was easier for the plane to climb up. So most of our flights, you'll see something like this, where we start at 36, 37, up to 39, and then go up to 40s.
Can you swap instruments during the flight?
No,
No.
these are gigantic instruments and,
And
it
you
was-
open back, kick them into the plane?
yeah, exactly. You can't, it was, the environment inside the plane was very tightly controlled. There's a lot of things that we couldn't do that you do normally in a normal plane. And yeah, moving instrument was not allowed. Open air canister of sodas got allowed. If you have tool boxes, they had to be in a certain place and in a certain position. So there were a lot of rules and regulations that was.
These missions were 10 hours each. How
Right.
often did you do them? I mean, what, they're bi-weekly, monthly?
4 times a week.
Four
So
times
when
a
we,
week?
yeah, when we started the mission, we were less, we are doing 2-3 times a week. Because again, there was a fear that we may break the plane. And the other bad thing for us was by the time the mission started, the science mission, there were only 7 747 SPs in the world. We already had 2 of them. So basically, we were scavenging the rest of the world for parts because our parts would break down. And I can tell you stories about how we went to New Zealand and our engine developed a crack. And we had to send a new engine all the way from Palmdale back there, remove the old one, put the new one, and then fly again the next night. So it was, I mean, the stuff those engineers did and the maintenance people did was just incredible. But yeah, we were always running around looking for parts. And here is the entire lifetime of SOFIA. This is the flight tracker, and different colors means different years. So you'll see that majority of our flights were over continental US and the waters around it. Sorry. So that's where that is. And as I mentioned, in our summer and southern winters, we'd go down to Christchurch because that's where the Antarctic Center was, and they had the facility to support something like SOFIA. So we'd stay there for about 2 months and do our observing from there. There were a couple of observation on this coast, on East Coast, and this is a very unique flight that we did, which I was on. And this was a flight where we wanted to see an occultation of Triton. So Triton going in front of a star. We wanted to measure the atmosphere of Triton. And as the Triton went in front of the star blinked, and we could see the light coming from the atmosphere of Triton. And I have a video later which I'll show. But then in 2020s, after 2020s, when we had COVID, the New Zealand government said, best of luck, but you can't come here. We love you, but you can't come here. So those during the COVID time, we went to Fiji and we did a couple of missions from there. And the next COVID year, we went to Chile. And here are the flights from Germany. We would go once in a while to Germany for heavy maintenance of the telescope, the plane. The heavy maintenance was done in the Lufthansa facility in Germany, and we do some science flight out of it. So all these are just purely science flights, some 700 odd flights. Yes, sir.
How were missions decided? I mean, because you did an awful lot, and so was it just a whim that said, hey, let's go do this? Because how many astronomers are involved?
I wish it was whim, and I wish they had left it to me. Then I would have done only molecular clocks and nothing. No, SOFIA worked just like any other observatory that NASA manages, or we astronomers manage. And the way things work out is that every year we put a call for proposal, and what we tell is that the astronomers from all over the world can apply for time on telescope. And so let's say you have a project, you want to look at, I don't know, Jupiter and look at the giant red spot for 2 hours. So you write a proposal and say why you want to do it, what is the scientific reason you want to do it, how you are going to do it, also why it is important, all those things, submit it to us. Then we collected a panel of judges or reviewers from the community of astronomers and sent them all the proposals, and they get to grade it, like have to observe if we have time, and no, this proposal needs a lot more work, we can't observe. So we collect all those. Then we had a scheduler, an automated scheduler, which would take all these information, what altitude they wanted, what time of the night they wanted, and it would prepare a schedule of how you're going to observe. And as you saw earlier, every night we could observe maybe 8 or 4 to 8 different sources with 2 calibrators. So it was all decided by the ranking of the proposal and what was available at what time of the year and where we were. Does that make sense?
Yeah,
Kind of.
thank you.
Now, are these missions fully funded by NASA or joint with Germany?
80-20, yeah. 80 by NASA, 20 by Germany. And Germans had their own, they had some instrument, we had some of our instruments. So it was a collaborative thing.
Is there special skills to turn the plane? Looks like hairpin turns up there.
No, I mean, on the screen, it looked like a hairpin turn, but it's not that turn. It's a gentle curve. And the pilots are NASA pilots. They're professional. They have been on the business for a long time.
The training.
They had thousands of thousands of hours of, flying planes. And every year they had to go to Denver to get flight certified. And that's the only place. I don't remember the name, but there's a flight center in Denver where they would sit. I got to go there once. It's basically a simulation. You sit in this machine and you get to fly the plane, and it, it behaves like a plane. You get a test. Well, I crashed the plane, so it's okay. That's why they didn't let me up in the cockpit. But I've been in the cockpit. I'll tell the story later. Anyway, why do we need to go up that high? Why can't we just do it on the ground? What's the advantage of going to stratosphere? And this is an example here which tells you why we need to go up. So if you are in the best sky in the world, let's say on Mauna Kea, and you look at what I'm plotting here on my y-axis is transmission. Basically what that means is the light coming, say, from a star, if it is 100%, then if the blue line is near 1, then 100% of the lights come to my telescope. And if I'm somewhere here, like at 16 micron or around 100 micron, none of the light can come to me because everything gets absorbed by my atmosphere. So basically what this is telling is how much of the light gets absorbed by the atmosphere. So if you compare Mauna Kea to SOFIA, you clearly see that all the windows in the far infrared just opens up when you go up high. And all you need to do is go up to about 40,000 feet. And then you can start observing from all the way from, about 20 micron all the way out to like 1,000 microns. And the infrared astronomer always talk about wavelength of light, but in terms of microns, because that's what we measure it in. If you talk to an optical astronomer, she may talk about angstrom units of wavelength. Basically here, I'm talking about electromagnetic spectrum, and the wavelength of light in the infrared wavelength usually goes from 0.7 to 1,000, and then it becomes micro. And these are tiny numbers. So to give an example of how big that is, the image on the side here, this is an image of a normal human head. And the line here that you see is about 20 micron wide. So we are talking about really small oscillations of the electromagnetic radiation. That's what we are saying. And on the other image, you'll see all the missions that we have, that we had in the past and that we have, that are observing in different wavelength regions. And when I look at this image, I usually stop and step back and look at it, because on a normal given day, I just wake up, drink my coffee, and go to work. I sit in front of a computer, I look at some data, and I play with it. I don't realize sometimes that how lucky I am to do that. And it's not because there's something special with me, it's because there was always people who helped me along to get there. And this is my thanks to them that I had the good fortune to work with Spitzer, starting with Spitzer. I worked with SOFIA, then Hubble, and now JWST. And all because of this group of people who came and helped along each other, and we went and did this. So this is, I always have to stop back and think, oh, this is why it's important. This is why we do what we do. All right, here is, this audience definitely doesn't need this introduction to this object. What I would call your attention to is the 2-star, Betelgeuse and Rigel. And one is a red supergiant, the other one is a blue supergiant. And this is a visible image of Orion. And you have your classic Orion nebula and everything. But if you look at the same in mid-infrared, this is what you see. All the stars are gone. There's no stars now. There's only gas and dust. That's what you're seeing. You're seeing the warm, not the hot stars, but the warm dust and gas. That's what it's glowing. And this bright yellow objects are the places where stars are being born as we speak. The other reason I like this image is keep your eyes on Betelgeuse and Rigel. As I said, this one is a red supergiant. This is a blue supergiant. And when you go to your infrared, Rigel completely disappeared. You don't see it. Why? Because it's a blue supergiant. By the time you come to infrared, it's not emitting anything. Whereas Betelgeuse is a red supergiant, so it still has emission in the infrared. In fact, a couple of years ago, you may have heard all of a sudden that Betelgeuse went very dim. What happened? So it's a supergiant. It's a pulsating supergiant, and hopefully soon it will go nowhere. That'll be fun. Yeah, again, a demonstration of what you see from the visible light and what you see from the infrared. In infrared, you see all the deers, and visible, well, only a few of you will probably see what's in the sky. So SOFIA has heat vision. Basically, that's what it is. But we are not like Supermans. We don't shoot light from our telescope. We are more like predators, where we see the infrared compared to the other background. So remember that. Okay. So now we have our different instruments that I was talking about. So these are the 5 different instruments that, yeah, there was another one which was retired. But anyway, these are the 5 different instruments that are mounted on SOFIA, and it could do different things. Forecast was basically a mid-infrared imager. It imaged anywhere from 5 microns to about 30 microns. GREAT is a heterodyne receiver, so it takes spectra, a very high resolution spectra. PPLS does a spectral cube. That means it takes images and spectra at the same time. So you have a 3D image of the object. HAL Plus, one of my favorite objects, is the only one that does imaging and polarimetry. So we can measure the polarization or magnetic field of various objects.
Yeah.
Question?
Just put my old hat on for a second. Hey, for everybody online, we're not monitoring the chat. So if somebody's got a question, please unmute and jump in. Thank you. Back to you.
Thank you.
I got a quick question.
Sure, go ahead.
So I was wondering, how long are you able to like point on a single target for? You said that the telescope has a small field of view of like 2 degrees.
Yeah.
So how do you guys like move the airplane to point on a single target over like a span of time?
It depends, because it depends on how fast the object is moving. If it's a slow moving object or a fast moving object, depending on its altitude in the sky. But for example, when we did the Triton observation, we could sit on Triton for about 3 hours. I think that was our maximum that we could stay on an object. After that, we had to move the plane. And when I say sit on the object, it's not a straight line. The plane is not going in a straight line. We do gentle motions and turn the plane a little bit to keep the object in that window of 2 degree by 2 degree. Does that make sense?
That makes sense. Thank you.
Okay.
Arjun, that was you?
Yeah, that was me.
I haven't seen you in a few months and your voice is changing.
Really?
Okay, great.
I'm running late, so I'm gonna rush through these now. So again, here I'm plotting the resolving power of our instruments versus the wavelength, and you can see forecast and XCs and all the instruments. The reason I like to show this is that SOFIA is the only instrument that sits right between JWST and ALMA, which is in the microwave region. And you probably, and with the demise of SOFIA, everything from 20 micron to about 400 micron has disappeared. We don't have a facility now to do that observation. And you'll probably ask, well, what's the big deal? I mean, we still have the lower wavelength and the higher wavelength, and we still have instruments which we can see. But if you look at the spectral energy distribution of our galaxy, so what I'm plotting in this is on my y-axis is what we astronomers call SED. It's basically how much energy is coming out at these given wavelengths. And if you notice, the spectral energy SEDs peak at about 100, 150 microns. that is the place where SOFIA was the best at observing. And all those emission lines, the green ones that you see, that tell us something about the dynamics of the gas and dust in our galaxy. So with demise of SOFIA, we now are blind between 20 and 400 microns. Yes,
Is there a plan to fill that gap again with something?
there is, currently there are no mission that will go in this wavelength range.
Why are they discontinuing the missions? I mean, it's national.
Money.
Yeah.
I mean, as I said, SOFIA is expensive and there are a lot of new missions coming up. So, I mean, people at NASA have to make those kind of decisions. I mean, I'm glad I'm not in that, like it's way above my pay grade, but they have to decide on cutting something and supporting something.
They put it in mothball, so if you get funding, they could resurrect. the mission.
No, SOFIA cannot be resurrected now because the SOFIA is completely gone.
No.
Yeah, SOFIA went off. So if we do a SOFIA, it will be completely brand new mission, brand new development. And
New plane, whatever.
yeah. All right. You good? What are the differences between these two images? Anyone online? Do you see the difference between these two images?
Yeah, the one on the left is greener.
Okay, other than that, don't worry about the color.
The one on the right has an extra star in it.
Supernova. Very good. One on the right has an extra star, and that's the supernova. This is M82, and 2016 there was a supernova in M82. And the reason I like to show this image is because I'm a weighing person. I'm very proud of this image because this is my image. And it's not only my image. This image was taken by the instrument called FlightCam. And this was at the very early stages of SOFIA, and I was writing a pipeline to reduce all the data and have it publication quality, basically fully calibrated. And that takes a lot of effort. It's a really big code. And we observed this on the flight. It was one of the first observations we did on the flight. And by the time we landed, I had the data ready to be used by astronomers to publish the results. And for one day, I became very famous. Everyone in the infrared astronomy knew me. But we did a lot of other fun stuff. This is M29. It's a planetary nebula, and this is a late stage of stellar evolution. Each of these are taken from a forecast instrument, and I have labeled which wavelength we are looking at. So as you see, as we go at longer and longer wavelength, we are looking through the dust. This object has two bipolar outflows you are seeing on top and bottom, and we are seeing deeper into the cloud and looking at the star itself that is being formed. But before I show that, I should tell a brief note about infrared astronomy. Infrared astronomy is not like visible astronomy. Normally, what you do is you point a telescope at your object and you start taking images. And you'll probably stack it in the end and make a beautiful picture, or you'll calibrate it. At most, you may dither a little bit so that if there are bad pixels, they get blurred off. But other than that, you don't do much. But infrared astronomy, that doesn't work. And why doesn't it work? Because the sky itself is bright in infrared. Sky is warm. It's not 0 degrees. So it has heat. So your telescope is an infrared telescope. So it is not only looking at the object that you're observing, but it's also looking at the sky. And the sky is so brighter in the infrared compared to the object that it basically washes out everything. So when you get your first images in the infrared images, you don't see your object. The second thing is your telescope and the optics are warm. Even though we cool the instruments and everything, and even though we are at 40,000 feet and it's minus whatever 100 degrees outside, it's still not absolute zero. It's radiating. And you have to have a method to remove those emissions. And here is what we do. We use something called as a chop. So we use two different chops. So we move the secondary mirror, we chop it at a very high frequency. So at one point, it looks at the star, and then it looks at the sky. And we do this on a very fast time scale. And when we subtract one image from the other, we have removed the sky. And now we have just the source and the telescope. So here is an example of that. We are in node A position. So the object is This one, we are looking at the object, then the sky, object and the sky, it gets populated. You subtract on source and off source, you get the chop difference. Then what you do is you move the telescope and get the sky now as an on source, and you do sky, source. You populate the second north position. Again, you subtract one from the other. You get the sky subtracted image. And then when you subtract the last two, you are getting rid of all the telescope emissions.
Wow.
And in the end, you have your net source signal, which is a tiny gas and dust image.
You don't have to do the same thing on the web though, because the web is insulated with all those reflectors and things.
Even web doesn't do the chop and not because it can do, but we take the off source position. So we look at the source and we do the off source because there's always background emission in the
But
infrared.
it's
So
just
we
not
have-
as significant
Right.
as this.
But with web though, you're outside,
That's
you're
correct.
outside the
Yeah.
sky,
Yeah.
so you don't have the
It's
sky.
right.
gas.
Miles away from it.
That's right. So it's not as bad as Sophia, but there's always background, and to remove the background, look off source, somewhere off source. All right,
So how fast is fast in the chop?
10 hertz.
Okay.
We are chopping at 10 hertz.
Yes.
And then we chop at 10 hertz, we move, and then we chop again 10 hertz. And we do this multiple times. So we'll have maybe hundreds of images before we collapse them all together. Quick few science cases.
One more question.
W51. This was one of the most massive young stellar object that we have seen. It sits somewhere right in the middle here. In fact, this whole entire region has massive young stellar objects, and it is really hard to study these guys because they're so massive. Their lifespan is very short. They evolve very fast because of gravity. Everything falls down and goes up. So we have to catch them in action. So there it is.
I have a question on that.
Yes.
So the lifespan is very short, but, you know, in astronomy, as you know, short is, could be
Yeah,
millions
short
of
is-
years. So when you're looking at stuff, why is it so difficult to capture? Because it's not changing from day to day, right?
It's not changing from day to day, but even if you look at statistically across the sky, you will see more of the long-lived, and there is more probability of you catching the long-lived ones than the short-lived ones. It's just because they evolve so fast. And even though, yes, you have the entire sky to watch, not all are bright, not all are in the right position for you to see. So when you look at the younger stellar objects, not the lower mass stellar object, there are lots of them and you see them all the time. Whereas the faster ones are hard to see because you need to get that statistics. It's a game of statistics more than anything. And this is an image, but it's taken as a spectra. It's a spectra of C2 line, doubly ionized carbon line. And this is a spectral line, so you can measure the Doppler shift. So you can see what the object is doing, whether it's moving away from us, close to us, things like that. And this is about 2 million spectra taken of, this is the Orion cloud. And the beauty of this is, once we have this, we can use this as a 3D object and move it around to study how the Orion looks, say, from the back of it. So all the red and blue are basically Doppler shifted spectra that you can observe. All right, I have lots of those, but I'm going to stop here. This is the image of, again, Orion, but the lines that you are seeing are measured by our Hawk instrument. That is the polarization line. Those are the magnetic field lines. So we have just joined, like originally, this is how the data looks like. But if you connect all those lines, this is what it happens. So now you know how magnetic field control the star formation. Here is the galactic center. The wide white things you're seeing are the dust and gas that is falling on the central black hole of our galactic center. So this basically told us, and earlier I told you, we just didn't look at Jupiter and M82. This is the crowning glory of SOFIA, to measure the magnetic field of the objects to understand what's happening and the dynamics of those objects.
Do you have someone whose job it is to render those images from the data?
There are two things going on here. So one thing is, yes, we do have a public outreach coordinator whose team does the pretty pictures. But these, to be honest, I don't care about this thing. This is what I care.
Yeah,
As a scientist, for me, this is important.
yeah,
But when we are trying to get the idea across of what the magnetic field line is, which is, remember, is an abstract quantity. It's in our head. It's a model of how we think the magnetic field and electric field works, right? So this helps in that. Does that make sense?
yeah, absolutely.
So when you know that, then what is the relevant importance from what you've learned? How is it used?
It depends. Like we try to understand things like when there is a molecular cloud and it's collapsing into a star, what makes it collapse? Is the magnetic field accelerating that collapse, or is the magnetic holding that? So there are two competing forces now: gravity, which is trying to crush it, and magnetic field, which may be trying to hold it. So we try to understand that at what stages of the evolution one overpowers the other. When does a star form? That's what the magnetic field tells us. The one with the center of the Milky Way, we, like years ago, we first looked at with forecast, and we did see the thing spiraling onto the black hole, the 400 million solar mass black hole. But we didn't understand what was guiding that. And with these images like this, we could figure out it's the magnetic field lines which are sort of guiding the material falling in, and on the outskirts they are all spreading out. So basically, it's trying to understand the dynamic of the system, how things work in space. It's not just gravity; there are other factors that are important.
Is that a DC magnetic field, or is that a
It's the electromagnetic field that you're
so it's
talking about.
in the infrared?
Yeah,
Okay.
it's in the infrared magnetic part of
The
it. So
magnetic.
what we do is we take the infrared radiation, it's electromagnetic radiation. We split it into two, ordinary beam and extraordinary beam. And each of them goes through a different half wave plate. We basically put different angles and we measure what their intensities are. And then there is a mathematical construct which you can use to combine them all together. And if anyone here is from college or high school, this is basically Maxwell's equations. That's all there is. There are 4 equations, and that will tell you everything you need to know. But best of luck understanding those 4 equations. All right, since I'm running out of time, I'm going to show this video. Hopefully, people outside can see this. This was when we were doing the observation of Triton.
Researchers of the Flying Observatory SOFIA, the Stratospheric Observatory for Infrared Astronomy, were in the right place at the right time on October 5th.
That's me.
When Neptune's This eclipse-like event, called an occultation, provided researchers the perfect opportunity to study Triton's atmosphere as the Neptunian moon cast a faint shadow on the Earth's surface. The team aboard the specially
That's
advanced
Grandpa.
747 SP aircraft observed the star's light as it passed through Triton's atmosphere using the onboard telescope and instruments.
We wait for Triton to pass directly in front of a star. It takes us something like 18 months to predict when this is going to happen. And if you get very lucky, or perhaps very skilled with the pilots, you fly right through the center of the shadow. In the center of the shadow, you get a deep view of the lower atmosphere from all around the planet.
But they had to
And just to give you an example of how hard it is to do these kind of things, Triton is really small object. And we want to catch, basically we are doing what solar eclipse people do, right? They travel to the different part of the world to be on the center line so that they can see the eclipse. We are doing the same thing, but now we are doing it Triton and the really far background stars. As the Triton moves in front of the star, we are looking at the star. We are not looking at Triton, and we are measuring the star light. And as Triton moves, it extinguishes. It goes off, it becomes an eclipse, and then goes off. And the speed of Triton is really hard. It's something like 16,000 meters per whatever per hour. And so it's going very fast. It's going over the Atlantic Ocean. And the totality that usually people talk about in eclipses are in minutes. This was a few seconds. So we had to have a plane flying at 0.8 Mach in that few seconds in that place.
And you were flying in the direction that made it the longest?
The
for you?
longest, yeah, you have to do that to be in that thing. And when first, Sophia first did a similar operation of Pluto, and when we planned that, none of us expected we'd see the eclipse. Because it's just not possible. It's impossible for a plane to come to that kind of accuracy.
How wide was the,
It's quite wide, it's about 20 kilometers.
oh, okay.
Yeah, but it's the thing is not about the wide, how fast it moves. It's gone in a blink of an eye. But the pilots are so good. By the time we were doing this, they were so good. They could get us right in the center, not just in the eclipse shadow, but they got us right in the center line. And what happens if you're right in the center line is that the light coming from two sides of the planet, from the atmosphere, they get enhanced and you see this small flash. And if you catch that flash in different wavelengths, you get to tell what is in that atmosphere.
Wow.
The grains and the size of the grains and stuff. So anyway, I'm gonna stop here because I already went way overboard with
No,
my
you're good.
talk.
You're good.
I'm good?
Yeah.
Okay, I'll continue.
About an hour.
Finishing this.
More than 37,000 miles per hour, while the aircraft traveling at Mach 0.83, nearly 636 miles per hour, position the team inside the shadow center. Researchers, flight planners, mission directors, and pilots all work together to get Sophia into the shadow center during just 2 minutes.
I'm looking for you now.
I'll point out.
Researchers are analyzing
That,
the
did you see me in the corner?
That's it.
Too fast.
Too fast.
It's one of those short-lived astronomical objects as opposed to the long.
So nobody asked the most important question. Did you
Yes.
get little bags of peanuts or little bags of pretzels?
Oh, man. Let me shut off my mic so that there is no echoes. Forget, when we first started flying, we didn't even have coffee on board. They wouldn't even allow us to brew coffee because they're like, who knows, something will explode, or you will spill it somewhere. It took us about 4 years to convince them it's okay to have a coffee machine inside. So peanuts, forget peanuts.
Will they give you a barf bag?
We not only had a barf bag, but we used to always carry something called as EPOS. It's an emergency thing where it has a small oxygen canister and it's made of like a very high, I don't know, mylar kind of thing, which is like it's basically I don't know how to explain. It's like a plastic bag. You open it up. If there's an emergency, there is smoke in the thing, you open it up, you put it over your head. It has a rubber band that sticks to your neck and the canister opens up and there is oxygen inside. So now you can walk out of the plane when there is smoke in. And they made us practice this on the ground. Luckily, we never had to use it. But even if I had to get up and go to the restroom or whatever, I always had to have that bag with me. And Lord forbid, I forget it on my seat. The mission director is like, "Where's your EPOS?" Okay, I'll wear it. So,
Did you have any other kind of training, like survival school? Like, I went through survival school.
When we first started flying, before science, they used to have the training about how you jump out of the plane with your hands or
Really?
no things on your wallet and all those things. But later on, I think they're like, hey, we have astronomers are dime a dozen. We use a couple, it is okay. So no, I didn't have the opportunity to go through the whole training, but we always had to go once a year. We had to go through the regular emergency training. And yes, they did have a barf bag. And we were told that if you use it, it's yours to keep. You have to take it out. You can't put it in the trash because there are no trash in the plane.
So for 10 hours, you can only,
That's a rough time to not drink coffee or
We,
eat anything or.
we started taking, I mean, we always had water and stuff,
Yeah.
so we didn't have coffee. But, you know, as an astronomer working through the night, we are so used to drinking coffee till 3, 4 in the morning.
Yeah.
That was the biggest complaint we had.
Yeah.
We are like, we are hungry, that's fine, but give me coffee. But later on, things got relaxed. Right? The thing was, when we first started, we didn't know anything. Like, how does this work? Is it okay or not? So later on, we could bring food. We had sandwiches and cookies and stuff, and then they had coffee. But for example, when Great Instrument was flying, it is in the almost heterodyne. It's in the microwave region. That time, you couldn't use the microwave or the coffee machine because it will interfere with your observations. So those guys were really.
But could you use your cell phone during takeoff and landing?
They didn't allow cell phone either. We all had Macs. We listened to each other through the headsets that you saw on the video. Any questions online?
Just so you know, there's nothing in the chat, so I don't know
Okay.
that there's any questions.
Thanks, Wayne.
So what did you find? What is in the atmosphere of Triton?
That paper is still not out.
Okay.
I'm gonna wait. But we did, the only thing I can tell is we did see the central flash because we were reducing the data, roughly reducing the data as we were going on. And we did see that when the eclipse started and ended, the angles or the slopes of the eclipses were different, basically suggesting there are multiple layers of the atmosphere and it's not just one big atmosphere. So that's the only thing I know.
You say that it's been completely dismantled, Sophia, and it can't be resurrected.
Yeah, okay, so what happened was in the lifetime of Sophia was 20 years. So it was supposed to go from 2012 to about 32 or whatever. But in 2022, NASA decided that Sophia needs to be shut down completely. So they gave us an year to shut down it in an orderly fashion. And at that time, once that came in, basically there was no money to keep Sophia. So
You said it was 80 million a year?
about 80 million.
Yeah.
Where's the mirror?
Seems like
The
money well
mirror has
spent.
gone back to Germany, I believe, and they're going to put it in a museum.
Yeah.
The telescope with the telescope mount with Sophia, the plane, is in Air and Space Museum in Arizona, in Pima Air and Space Museum.
Really?
Yeah, we in fact we just had a reunion there, and about 400 people who had worked on Sophia showed up for that one day in Air and Space Museum, and it was pretty bittersweet to see the plane the way it is now. I mean, it's still the same. When you go inside, it still looks the same, but there are no instruments. All the computers are now gone. It's just a shell sitting there, and you thinking like you worked there for 10 years. So yeah.
Do you have a favorite bit of science that you accomplished or over the lifetime of the mission?
There were a couple of them, like discovering the water on the moon was very important, I think. We discovered the first hydride molecule in space. That was very important. But I would say there are about a dozen or so. I mean, depending on which astronomer you speak to, she or he will pick their own favorites. But these were some of the stuff that I had the good fortune to work with. So
Do you feel the science is hurting because we lost that spectrum now?
yeah, that is the general consensus of most of the infrared astronomers, because they lost, and they had all these plans to do all these different projects, and now we have to wait for however long it takes to build the next mid to far infrared facility.
Recently, they said there's caves on the moon.
I don't know about that.
I'm waiting for the tunnels.
So are some of the photos that you showed, especially the electromagnetic spectrum and everything, are they on the NASA website? SOFIA website?
You should, there is a SOFIA website still on NASA, and all the images and all the publication is listed there. So you can, there are thousands of them. So
My last question is, does Frank Summers still have an active role in all this?
When you're seeing the video, there was an elderly gentleman who was standing there, and I said, that's grandpa. I call him grandpa. That is Eric, who basically he started infrared astronomy. And he had the vision of, he has worked with Kuiper, he has worked with SOFIA. And even now, in the last days of SOFIA, he would come and fly with us. Wow, yeah.
Astro dude,
Sir.
this was an awesome presentation. Thank you very much.
Yeah, thank you.
I would
Thank you
like to
so much.
I wholeheartedly agree. Thank you so much.
Thank you.
So now I'm gonna go back and share.
Who's that?
Yeah, thank you once again. That was really fantastic.
Thanks.
So,
I can keep talking about Sophia. There's no end to it. I have plenty of most fun stories. We can talk afterwards, I guess.
That's fun.
okay, well, let's move on to the rest of the meeting. Maybe we'll have some time at the end, especially for those in the room. Jim, are you online? Please say
Yes,
yes.
I am.
Oh, good. I was afraid that I might have to talk to your slides, and you are so much better at it.
Well, appreciate that. And I did screw up one of the slides, but we'll do the best that we can with it. So at any rate, here are your shallow sky highlights for between now and our next meeting. Mercury is going to put on a little bit of a show around Labor Day. So if you're interested in getting up early, pre-dawn, you can get out there and catch Mercury. This is going to be its best morning apparition of the year. So it'll get it for us northern mid-Atlantic observers. This will be the ecliptic as perpendicular to the horizon as possible, so you get the best altitude. So that being said, it's still not, amazing. It'll be 8 degrees high as twilight starts. So, you can get out there a little bit, I guess that would probably be somewhere like around 5:30 roughly, maybe 5:45. It's going to actually, right now, at this period of time, it'll be larger than Mars, 7 arc seconds versus Mars's 6 arc seconds, and it's going to be brighter as well. So this is really a good opportunity to catch Mercury. And if you happen to be an imager, and you might try imaging the planet, and especially if you use an IR filter, you might actually, we have amateurs that actually pick up details, that can pick up albedo features on Mercury. And there's one there, that little bright dot, I believe that's Copeland. So that would be a challenge, but if you're up for it, give it a shot. All right, next slide, Victor.
On that one, Victor, if the weather is promising, maybe I'll open up Carr's Mill super early in the morning.
Where I guess I was spacing out there a little bit. Where in the sky do you have a 8 degree?
So for Carr's Mill, you'll be able to.
Which direction is it?
Which direction, Jim?
East. It's going to rise before the sun.
Oh, we got it. Perfect. There's nothing in the way.
Yeah,
Carr's
east
Mill
of
to the
work.
east.
Yeah, right.
It's perfect.
Well, that might be worthwhile then, maybe over Labor Day weekend have.
Yeah, listen, if the weather's good, we'll communicate.
Cool. Okay, Saturn is going to reach opposition on the 8th, which of course means that it rises as the sun sets and it's visible all night long. Right now and for the next couple of years, the rings aren't open very wide. But if you're an attentive observer, you're going to be able to see changes in the planet's appearance over the next few months. Basically, kind of as the Earth is beginning to rise like slightly above the plane, you can see in the animation below, the rings gradually open until they get about their widest between October and November, and then they're going to close back up again. So if you are observing now, you might be able to pick up a little bit of the shadow of the rings on the planet. There's August, just below the rings, you might be able to see it. And then as we rise up, the shadow will actually move inside. And you'll be able to see Cassini's division a little bit easier in October and November. So, not a lot to hang your hat on. But visually, if you're the sort of person that likes picking up on the small details, definitely a lot of interesting stuff with the way that Saturn is presenting itself over the next couple months.
And transits too, right?
We do. Transits, unfortunately, Titan has finished for this year. The last one of those was on August the 1st. If you're an imager or if you have a really large scope, you might be able to catch Dione in transit, but that's a little bit more challenging. All right, next picture, next slide. And my favorite, Jupiter, it'll reach quadrature on September the 12th. What is quadrature? Quadrature is when the sun is rising, the planet is on the meridian, and then you have eastern quadrature, which is the opposite, that when the sun is setting, it's on the meridian. So that's kind of like a hallmark in terms of when the apparition really kind of opens up and gets started. This is a current image from a really excellent observer down in Georgia. You can see the red spot's still around. It's definitely looking a bit smaller. And we're beginning to see a lot of ovals in the north equatorial belt. Click again, Victor. And normally the slide should have shown a different picture, but we'll just mention that there is, like, below the great red spot, and you see it just barely on the right-hand side there, there's a very prominent south-south temperate belt, which is kind of developed. So a lot of times when you look at Jupiter, you mainly see the two equatorial belts. If you're looking at the right time, you may actually see three belts because this thing is pretty prominent. Next click. As I mentioned, there are ovals forming in the north equatorial belt. So that's the top thick belt. So that's something that, and they're large enough that I think you might be able to pick them out visually if you have like a 6 to 8 inch or maybe larger scope. Next click. Click again, Victor. I think there's one more.
Sorry, I'm
That's all
struggling.
right. And again, the great red spot has its orangish color. It's as small as it's ever been. And the other thing you can see here, notice that, and this you would definitely be able to pick up too in moments of clear seeing, that major rift. And this is only 2 weeks old here, this picture. So really major rift. But this is what's so great about Jupiter is, you can go out and something totally unexpected like that you'll pick up on. So, and there's even a smaller one running more horizontally in the north equatorial belt below 3 ovals. So lots to see and look at with Jupiter. And if you're an imager, it's a lot of fun trying to pick up on these things. One more slide. If you're into planetary stuff, and I'll put the link in the chat, the ALPO has launched its new website. Lots of good information there about the planets and meteors and all that kind of stuff. We've got a nice gallery where your fellow amateurs contribute their work. So if you're interested at all in planetary stuff, bookmark the ALPO and come visit it a couple times a month to see what's going on in the shallow sky. And that will be it for this month.
Great, thank you. And you should also take a little victory lap in that you had a big hand in the creation of this new website. So that's pretty impressive too.
Yeah, it's been my baby, and I'm glad it's finally launched.
Yes.
I'm sure you can relate.
Yes, yes. Jim is making reference to the fact that the HAL website will be updated soon, hopefully. Okay, so let's move on to some astro images. And Jim, as long as your mic is hot, you want to go ahead? Oh, here we go, some transits.
All righty. Yeah, as I was saying, August the 1st was the last transit of Titan for this apparition. So the one on the left is in white light, and you can see this kind of highlights how Titan has got a fairly dark albedo in comparison to the cloud tops of Saturn, because it showed up as like a silhouette. Usually with Jupiter's moons, now I think Callisto is the exception. They appear white and you almost lose them when they're going across the cloud tops. And I was surprised when I did the processing, you can just barely pick out a tiny little shadow there. That's not artifact. That is actually the shadow of smaller moon Dione going across the planet as well. So it's really a double transit going on there.
You mean right here? I'm putting the laser pointer where.
Yep, right there. And then the other one on the right-hand side is taken in infrared. And this is where Titan has just moved off the limb. You're seeing the limb darkening. So now in infrared, it appeared as a white little dot. And again, you can kind of catch Dione's shadow up above. That time in IR, it's a little bit easier to make out. So this is kind of like the season for catching these little transits and stuff going on. It's pretty cool. Once, a couple more years from now, it'll be another 14 years before you can see anything like this. And this was Sunday, that we had 2 naked eye sunspots. AR 3780 is the big one down below. I forget what the number is on the top one. But that was my effort, with apologies to professionals like Phil, in terms of documenting this humongous sunspot.
It's very nice, actually. White light.
Yep.
Did a
Okay.
really good job getting the penumbra.
Thank you.
I got a picture that I took of this with the sea star last weekend. And I'm sitting there going, why do I have thousands of dollars worth of telescope and fancy filters getting into the upper number of this little sea star right here on my cell phone, unprocessed. Looks very similar. It's just unbelievable.
Yeah.
Technology is just.
I would like to take this, sorry, Jim, if you'll allow me. The club has a sea star that we lend out every month. And I've got it here. The person who was due to take it hasn't showed up today. So don't forget about that. Go on the website. There's a link that says Sea Star. You can sign up, and we can coordinate. I can hand it off to you, or normally we do the handoff here at the meetings. So just letting you know, this month the person hasn't shown up, or the second alternate isn't here either. So I'll have it, and I'll reach out to the next person on the list when I get home. So, but yeah, the Club Sea Star is something that's it's available. Sorry, go ahead, Jim.
No worries. And again, you don't usually see me do much lunar stuff, but I was out early one morning as the moon was waning, and decided to grab and got what I thought was kind of a nice picture here of Archimedes, which is the large one there to the left, and then Arstillus and Autolycus, I guess is how you would pronounce that, these Latin names. But the moon's always just amazing in terms of the complexity of the features, and it's basically almost each time that you look at the moon, you could come back at the same point of how far the moon is into its how many days old it is, and it'll look different. It's always between the tilting of the moon back and forth. Yeah, I miss Bob. I wish he would here. He could, no pun intended, but he could wax poetic about the moon and all the beautiful features on it.
I believe that's Cassini, upper right of Autolycus.
I think you're right.
You got 4 there.
Jim, it's almost like you knew how my slides were going, because the next picture is from Jared Case, and he didn't even submit this. I just took it off the Discord site, because after I saw yours and I saw this one, I thought, boy, you can really see the difference. Like, it's clear that he took this in the early evening, just the way the shadows are falling, as opposed to yours, which has the bright things over here on the right, and you took it in early morning. But what you were just saying is I mean, it's a different image scale, a different image, but it definitely looks, I love this picture anyways, because it's got a lot of three-dimensionality to it, and some of the, the mineral moon stuff is in there too, I think, with the a couple of these seas, these mare. But but yeah, these guys look so different. I zoomed in, maybe I should have put a zoomed in picture here of this little region. I'm talking about, you know. Like up
Yeah,
here.
it's a nice shot. Yeah, that's exactly the same region. Yeah.
Yeah.
Got it in first quarter where the other one was in last quarter, opposite illumination.
Exactly.
Yep.
Yeah.
You got Ptolemaeus in this too, is pretty prominent at the bottom there.
Down here,
Ptolemaeus.
down here. Yeah, I'm not a good, yeah, we need Bob.
Know the names of those other two next to it.
Yeah. Okay, and Harini, are you on the line?
Yeah, I'm online.
Do you want to tell us a little bit about this image?
So this is the Crescent Nebula. I took it for 204 minutes because I stacked it. It's 4,700 light years away from Earth. Its apparent magnitude is 8.8, and it's in the constellation Cygnus.
Wow, that is
And then
awesome.
it's a planetary nebula.
Very nice.
What did
It
you
was-
use to stack it?
I used it the sea star, and then it had this deep sky stack like option.
Stacker?
Yeah,
Oh.
the deep sky stacker.
Yeah.
I looked at that, and then I gave add images, and then I saw the Crescent Nebula that I took. So I tried to stack it.
That is fantastic. I think pretty soon we're gonna have to get PixInsight installed on your computer.
Yeah, it actually came out pretty good.
Yeah, it is very nice. Thank you for sharing.
And was that really 1,000 images approximately?
No. I don't know how many images I stacked.
Well, were there 10-second exposures, right, Harini? So you have 10-second exposures and 204 minutes of capture.
Yeah, the
That's
sub
accurate.
exposures was 10 seconds.
Right, so yes.
Wow.
That is fantastic. And where did you do this? Was this at Alpha Ridge?
No, it isn't at Alpha Ridge. We took it because it was a clear night.
You went out just in your neighborhood?
Yeah, in my neighborhood.
Wow. So that's really good. Thank you.
Thank you.
Okay, Jose, are you on the line? So Jose is not here, but Jose is also a relatively new, he's very, very new to the whole process of astrophotography, and he is coming on like a storm, calling impromptu star parties. He's a new superstar member of the club, and I'm really happy that he's part of the club because he's really excited about opening the park up. So here is one of his, I guess this is the Wizard Nebula. And Harini, he has a much bigger telescope, and I think he spent a lot more time. And he mentioned that this was his first use of PixInsight. So here is the same object with more time and a bigger telescope. Just so this gives you a challenge as you develop in your astrophotography. But this is a beautiful shot. I guess Jose's not here to talk about it, so I'm going to move on. And he also took the Eagle Nebula. And here's another shot that I took off the Discord page without asking. And this is the Eagle Nebula. And I just love the way that Benjamin framed this. You normally see real close-ups. If you zoom in, you can see the the features that you're used to seeing, the pillars of creation and whatnot. But I just like this framing with all that interstellar dust and whatnot. Wayne, Jim Johnson, are you on? Please be on. I want him to talk about this.
Wow.
Yeah. Jim, so Jim has, he's got the dream setup that I want. I want to steal his camera and filter wheel. And he has become quite the astrophotographer. And he said something to me in his, I didn't remember the details that he sent in his email. But this was, it's obviously, the squid, this is the bat, I think they call it the bat and the squid. The squid nebula, you normally see it in a different color, I mean, images that I've seen, but he chose to make it blue, but that's oxygen 3. He used narrowband filtering, oxygen 3, and I think the brownish reddish is hydrogen and sulfur mixed. But I don't really know exactly how he did this, but I just think it's a really, really beautiful shot. That squid is really faint. You have to spend, I think he said something about 17 hours of data collection just of O3 and his skies, which are like Bortle 5, I think. So anyways, I love this photo. It's beautiful. And Jim, once again, amazes us with his work. And then is talking about amazing. This is Jared. Jared, you're not on, are you? He's got family things on Tuesdays or on Thursdays. But Jared took this, and I don't have the details. But I do know that he took it from in Hawaii on the top of a mountain. I don't know what he used to capture it, but it's so nice. All the detail. You can even see like lagoon nebula in there and some. It's harder to see on my screen, but there's so much. All this cloud around Antares and Scorpio, and it's just if you know. I don't know if you can use this in your research, but there's molecular cloud information in here. Anyways, that's all I have for astrophotos this month. So I would just like to say thank you to everybody and to our speaker. And I'm gonna end the recording. I think we're finishing a couple minutes earlier. Then we need to get out of here they're going to close this place at 9. But if the folks in the room want to stick around and chat for a little bit, I think that would be nice. I would definitely like to talk to a couple folks. So thank you all for coming, and thank you again to our speaker.
Thank you.
Bye.
I'll leave I'm going to stop recording, but I'll leave the camera on.